Welcome viewers to the 11th lecture of the course Metal Cutting and Machine Tools. So, as I had declared the last in the at the end of the ninth lecture that I would be covering the leftover part of the ninth lecture in the 11th lecture, and I would be dedicating the 10th lecture solely for numerical solution of numerical problems. So, in the last lecture we had some leftover portion of measurement of cutting tools, and I will discuss that very quickly and then move on to the discussion of tool life and wear of cutting tools. So, to start with, when we were talking of measurement of cutting forces, we discussed the theory of strain gauges and the fact that the strain gauges have a compact. So, we had discussed the theory of strain gauges and understood that dr by r divided by the strain equal to gauge factor was roughly equal to 2, which showed that there is a relation of proportionality existing between resistance change and change in and strain. So, this proportionality allows us to measure resistance and accordingly predict what is the strain, and that means within elastic limit what is the stress, and from that what is the force. Naturally, with some known force values we have to calibrate the machine, so that we understand which particular which particular change in resistance stands for what particular force. Now, how do we measure this change in resistance and utilize it for our values? Just use of a single strain gauge will not make the change in resistance. So, we cannot register, rather it will not register a marked change. So, for that what we do is we can employ a number of such strain gauges. For example, in this particular structure, shell type structure, as you can see, the front body and the rear body, they are connected by some horizontal beams. Okay. The whole body is integral. So, that if I apply a force downwards, say I am applying a force downwards, sorry, let me remove this line, it is not a straight line at all. If we apply a force downwards, in that case we will observe that all these will be bending as beams with the neutral axis somewhere here, and these are bending, and due to the moment caused by this downward force. So, if we have the cutting tool here, we are seeing the other view, side view here. If we have the cutting tool here together with this force acting as the main cutting force, we will be having the bending of all such sections. So, here also there is one such section, sorry, here also there is one such section. Let us see what is going to happen to this. When this is bending, this being the neutral axis, we will have a considerable amount of rather we will have no change, net change in resistance, because if the strain gauge is put here, part of it is above the neutral axis, okay, this part is above the neutral axis, it is going to register a tensile stress, and therefore, it is going to have tensile strain and resistance is going to become higher. In this case, however, it is below the neutral axis and it is going to register a what do you call it, compressive stress, and resistance is going to become less. However, if you consider this particular one, it is definitely going to be tensile. If you consider this particular one, it is definitely going to be compressive. This one also, since it is more towards the top, this is more towards the bottom, tensile, compressive. Now, what we do is, we generally suppose we have a power supply, DC power supply, and these are the strain gauges. So, if we put a strain gauge in tension at this place, a strain gauge in tension at this place, another strain gauge in compression at this place, compression at this place. Ordinarily, if they are all of the same resistance and they are not under any stress, this would register a 0 value. This is say a voltmeter or a galvanometer. Okay. So, this will register a 0 or a null reading. But what does it point to? It points to the fact that at this point and this point, the voltage values are the same, because the voltage drop through this, through that, and through this, through that, they are the same. So, that the voltage is same here, but the moment we put it under tension, the moment we put these two under tension. So, I might be connected say T1 here, T1. I might be connecting C1 here, C1 like that. Okay. So, that way if so this is also far away from the neutral axis. So, this also will be say T2, this one will be C2, C2, T2. So, if we put these in this manner, the advantage is this, that we are going to have a distinct drop here, which is different from this one, because this will be low resistance and this will be high resistance. So, voltage will be dropping considerably at this point. This will be high resistance, this will be low resistance. So, voltage will not fall so much. Okay. So, this way we will register a change here at this particular point and we can read off the value if there are graduations, and we can calibrate it with known values and we can easily find out. So, this way if we use such strain gauges, it will be easy for us to find out the values of the forces. But what about the force which is coming out of the plane of the paper, out of the screen? That means this force. This force will be captured by this strain gauge and the corresponding strain gauges, there is another beam on that side. So, there is one on this wall, there is one on the inner wall, there are two such strain gauges on the corresponding beam on the other side. So, they will capture this force. So, this is generally referred to as the two-dimensional strain gauge turning dynamometer. So, instead of the ordinary tool, if you have this device, then it will be good. And what sort of configuration should it have? If this diameter is made higher, if this diameter is made higher, then you are going to get more response, more strain, because they will be more and more away from the neutral axis. If this distance is made smaller, you are going to have higher rigidity, because the overhang is becoming considerably high here. So, all these aspects can be taken into account when we are designing such a strain gauge, strain gauge dynamometer. So, dynamometers are devices for which can be used for measurement of forces, and here we are employing them for measurement of cutting forces. So, let us see what we have in store after this. In a similar fashion, we can also have drilling dynamometers. In the drill, if you have perfectly made cutting lips, sorry, if you have perfectly made cutting lips of the drill which are symmetric about the central axis, there would be no, the forces will be balanced in the radial direction. Okay. What do you mean by this? Suppose this cutting lip is experiencing this force and it is experiencing that force. So, in that case, this will also be experiencing this force and an opposite and hopefully equal force in this direction. So, this will be cancelled out, but this remains and this is called thrust. You might say, what about the force which is perpendicular to the paper, okay? Perpendicular to the screen? The force which is perpendicular to the screen, that creates a torque. While it is cutting, while it is moving, it is removing material, and the PZ component, if it is considered to be a single point turning tool, the PZ component creates a torque. So, that torque needs to be measured. Okay. Now, in this particular configuration, what happens is, we are having the drill coming from the top. This is the plan view. Okay. In the plan view, what happens is, just a moment, in the plan view, we are having 4 beams connecting up the central part, which is the job holder. This holds the job, drill job. The job is held here and it is drilled from the top surface. A drill comes and drills it, so that the thrust will be bending them as cantilevers. So, if you have strain gauge 1, strain gauge 1, strain gauge 2, etc. All these similarly colored strain gauges, they will be bending and they will be in tension, all of them in tension. On the bottom side, there are similar strain gauges which will be experiencing compression, and by the same discussion that we have had, they will be registering, if we can connect them up just like this Wheatstone bridge, okay, that is compression and compression on these two sides, tension and tension on these two sides, we will be able to measure the value of the drilling thrust in a very elegant manner. Just a moment. Yes. So, this is the way in which we can measure the drilling thrust. What about drilling torque? When the job is being drilled, this is the direction of the torque which is applied by the drill on the dynamometer, and the dynamometer beams bend. When the dynamometer beams are bending, this one will be experiencing tension, compression, tension, compression, and from here once again, if we connect it properly on the strain measuring bridge, this will register a change from the null position. Null position means here there is absolutely same voltage occurring here. The moment they are in compression and tension, this will be registering a change, and from that change with calibration we can estimate how much is the drilling torque. All right. So, these are some of the ways in which cutting forces can be measured. Now, I have some discussion on other types of dynamometers also, but I will skip them and upload them as notes, offline notes, which you can refer to, okay, like milling and grinding dynamometers, etc. Those I will come back, but let me start formally today's actual discussion. Today's actual discussion was on tool wear and tool life. What do we mean by this? Tool wear means that whenever a tool is being used for removing material, after a few minutes of use, if you take out the tool and look at the tip of the tool, which is defined by the intersections of the principal flank, auxiliary flank and rake surface, we will notice that it has undergone a change. Why so? This is because when we are this is because the tool will be deteriorating in quality when it is being put to use, where the chip is rubbing against the rake surface while moving and also applying a considerable amount of force, very frequently in the order of hundreds of newtons. So, the tool surface will undergo, first of all, a very slow process of wear and tear. So, if it experiences wear and tear, what will happen is there will first be rubbing of the principal flank against the tool surface, rubbing of the chip with the rake surface. Okay, so, bottom side of chip will be rubbing against the tool surface, rake surface, and the auxiliary surface will also be touched somewhat by the rubbing with the finished surface. So, when the chip is traveling over the rake surface, it tries to maintain its round motion along a circle sort of. Okay, let me draw this on this side. If this be the tool, initially it is a sharp tool and the chip is coming and moving. So, it tends to rub off this portion, and on this side the material the friction tries to rub off the flank, the principal flank. So, the principal flank is undergoing wear, where you can see there is a large notch at the side, because that is where the end of the chip is moving and it is having an edge. Edges always create a high amount of wear. So, this is the rubbing action of the edge. Here also a sort of edge will form, edges like these, and here I have tried to show a sort of a crater like surface, crater like feature on the surface. So, this geometric feature is slightly it is going down from the rake surface. Okay. It is a worn away crater. So, if this happens after some time, the tool will be rendered unusable. Why so? Does it not cut? Yes, it does cut, but there will be a number of phenomena which will be occurring, because of which the tool might not be usable after that. Generally, wear is not the only phenomenon which is going to occur. Catastrophic failure might be occurring due to breakage. Say in the very beginning itself, the tool is not very strong and we did not estimate it, and we have set it for cutting and suddenly it breaks off. That is to be avoided at all costs. Cutting edge itself individually might be dulling off very fast without any this effect manifesting itself before that itself. Those things we are not considering when we are talking of the gradual phenomenon of wear. This takes place very gradually. But when do we stop? When do we stop using it? What are the indications? First of all, I might be getting these are the indications: forces, exhibit, increase over time. Then other things might also happen. suddenly you find the surface finish which is obtained on the workpiece, it is not acceptable, it is deteriorating. Okay. Sorry. There might be vibration and chatter. There can be increase in power consumption, etc. There can be increase in the sound. There can be you know too much heat coming out from the color of the chips, etc. It can be found out. So, lots of indicators will be there showing that the tool has become reached a particular amount of wear. So, let us have a look. Yes, generally we are more interested about this flank wear growth. Flank wear growth has a limit after which we generally do not use these turning tools. I mean for that matter all tools, say in case of we are discussing our keeping our discussion restricted for the time being to turning tools now. So, what happens is when the average flank wear, what do we mean by the average here? It is not that notch, it is something to do with this value perhaps, average flank wear, and we sometimes call it VB. So, if we find that this value has reached a particular limit, we generally avoid using that tool and send it either for resharpening or we use another insert or another edge of the insert if it is of throwaway type. So, this value is generally restricted to 0.3 millimeters. Just imagine how small a value it is, but the cutting tool itself is very small, 0.3 millimeters. Now, how do we know that? We can either stop the machining and actually look at the tool and find out how much wear it has undergone, and from that estimate under a microscope or some device, or we can have some online devices which will be predicting that yes, the tool is now tool has now reached this particular value of 0.3 millimeters, or conditions similar to that have arisen. What is this particular curve? Let us have a look at it. Flank wear, in the beginning it grows, okay. When wear is setting in, there are lots of ups and downs on the surface. The surface in the microstructural level will show lots of ups and downs. These will engage with the workpiece asperities, and rapid break in wear will take place when these will be broken off, or they will be flattened or abraded, etc. All these phenomena will take place, and this is rapid break in wear. After that, once they have been cut down to size, there will come a region where a regular wear phenomenon takes place. Generally, if we have a cutting fluid, in that case cutting fluid can vastly change the behavior of contact between two say part surfaces. If direct metal to metal contact is there, in that case most of the time what happens is very rapid wear takes place. But if we can ensure that there is a particular lubricant put in between the two, then and if we can ensure that a film is created of a fluid in between, there is fluid film lubrication which can considerably reduce the amount of wear which is occurring between the two. However, once this particular wear phenomena regular at constant rate the wear phenomena has developed, after some time there is catastrophic wear when this cutting edge will collapse, because it is undergoing crater wear on this side, it is undergoing flank wear on this side, and therefore, it is separated by a very thin very narrow distance, and after some time rapid wear will take place when this cutting edge will be collapsing. So, in this case we set a limit 0.3 millimeters to be the average flank wear, after which we do not use the tool. Next. So, if we develop such flank wear curves, in that case if we use different values of cutting velocity, okay. Suppose I am using cutting velocity 1, I reach the 0.3 millimeters at this particular time. If I use cutting velocity 2, I reach this particular limiting flank wear, say 0.3 millimeters at this particular time. So, this way if I use cutting velocity 3, I reach that particular limit here. What is the relation between these cutting velocities? So, obviously cutting velocity 3 must be greater than cutting velocity 2 must be greater than cutting velocity 1. Why? If you use a higher speed, higher cutting speed, then obviously what will happen is it will undergo a higher rate of wear, which is shown by this particular curve. So, this is curve 3, this is curve 2 and this is curve 1, and correspondingly this is tool, the time for which the tool has been usable, that is tool life 3 here to here, and from here to here this is tool life 2 and that one is tool life 3. So, we understand that if we use a lower value of cutting speed, the tool wear is going to be slower and we are going to get higher tool life. You might say, what are the mechanisms of wear which are occurring due to higher speed, which are aggravated due to higher speed. So, wear will be taking place due to a number of reasons, and there can be different mechanisms of wear that we will be quickly having a look, but let us first finish the mathematical complete the mathematical relation between tool life and cutting speed, and after that we will be taking up all those particular relationships. Once we establish these particular tool life values. So, what is tool life? Tool life is the time period for which a tool can be used without attaining limiting flank wear of 0.3 millimeters. So, this particular time period is called tool life. So, I start with a sharp tool, I stop when flank wear, average flank wear has been reached of 0.3 millimeters. This particular time corresponding to that velocity of cut is called tool life. So, that if I now plot tool life on this axis, okay, T, I call it T. If I plot tool life along this axis and cutting velocity, let me call it Vc. In that case, we understand that there is a particular relationship expressed by this smooth curve, where this value will be equal to say tool life and this value will be equal to cutting speed. What is this particular relation? V is equal to V into t to the power n is equal to constant. This is called the Taylor's two-life equation. There is an extended form of that also, which we will be definitely looking at, but this is the basic relationship. V into t to the power n is equal to constant. Okay, so, C is obviously a constant and n for particular cases it will be constant. Now, what does it tell us? It tells us that if I use different values of tool life, I can get different values, sorry, if I use different values of cutting speed, I can get different values of tool life, and all of them can be satisfied, I mean can be expressed with this particular relationship. For example, if I use say a tool life value of 100, okay, sorry, if I use cutting speed 100 meters per minute, and I use a tool life of, sorry, not tool life, I have to find out the corresponding tool life for it. How can I do that? So, for that what we have to do is we need to have a value of n and we need to have a value of c. How can this be done? For example, you might be carrying out a number of tests. Okay, you can carry out a number of tests and solve for n and c. What are the tests going to be? Say at different values of cutting speed, we will be carrying out tests. But I do not know the value of n and c. How can I simply pass a curve? So, what we do is first of all we carry out a number of tests, and on a log paper we can plot those points and pass the best fit curve through a straight line through that. So, on the log paper, after we pass a line like that, we can have a linear relationship between the terms log v, n log t and log c. Okay. So, from that we can find out the values of n and c in a very simple manner, like reading off the reading of that line in the form of y is equal to m x plus c and then finding out the corresponding value. So, that part we will be taking up in our next lecture. Thank you very much.